Good day, class. My name is Sherilyn, and along with my partners JC and Mahendra, our presentation today will be on the tool Apache Lucene. We apologize for not being there today in person, but we do hope you enjoy our presentation. Thank you.
Developed by Doug Cutting, Lucene is a powerful Java search library that lets you easily add search to any application. Lucene is an open source, fast, high performance, and highly scalable text search engine library written entirely in Java. Lucene is a cross platform solution as it can be used in commercial, academic, and open source applications due to its performance, reconfigurability, and generous licensing terms. Lucene's powerful, easy to learn APIs focus mainly on text indexing and searching. It can be used to build search capabilities for applications such as emailing clients, mailing lists, web searches, database searches, and more. For the sake of time, I will not read through this entire list of Lucene features, but I will hone in on some of the more significant ones. Lucene calculates a score for each document matching a given query and returns the most relevant documents ranked by scores. It supports many powerful types, it supports many powerful query types, including phrase query, range query, Boolean query, and more. It allows searching and indexing simultaneously and provides pluggable ranking models, including VSM and Okapi BM25. Although there are many search systems available for use, Lucene has an impressive collection of properties that set it aside from its competitors. We found it interesting that Lucene is so highly employed by many Fortune 500 companies and larger corporations alike. In fact, according to the IDC, a remarkable 53% of companies using open source use Lucene. It has also been reported that Lucene is responsible for significant decline in commercial OEM revenue. Websites like Wikipedia, Twitter, Comcast, JGuru, and LinkedIn have been powered by Lucene. Lucene also provides search capabilities for Eclipse IDE, Nutch, and companies such as IBM, AOL, and HP. Lucene has been ported to many other programming languages, including Perl, Python, C++, and .NET. Here's a representation of Lucene's search system. In the following slides, we will provide insight as to how Lucene analyzes a document, indexes a document, and performs document search and search ranking through search queries and search scoring, followed by a quick demo to show how it all works. The Lucene Search API takes a search query and returns a set of documents ranked by relevancy with documents in which the best results are returned first. Lucene scoring uses a combination of the vector space model and the Boolean model to determine how relevant a given document is to a user's query. In general, the idea behind the VSM is the more times a query term appears in a document relative to the number of times the term appears in all the documents in the collection, the more relevant that document is to the query. It uses the Boolean model to first narrow down the documents that need to be scored based on the use of Boolean logic in the query specification. All searches are field specific because Lucene indexes terms, and a term is composed of a field name and a token. Lucene specifies a language in which queries may be expressed. For instance, Computer Not Java produces a query that specifies the term computer must appear in the default field and the term Java must not appear. Queries may specify fields as in text, Java, which requires the term Java to appear in the text field of a document. The query syntax includes basic field terms and modifiers for wildcard, fuzzy, proximity,
or range searches, and Boolean operators for requiring a term to be present, absent, or for combining queries with logical operators. Subqueries may be boosted by providing numeric values to raise or lower their prominence relative to other parts of the query. Queries may be constructed programmatically using the dozen or so built-in implementations of the OAL.search.query abstract base class. The query parser parses a textual representation of a query into a query instance. The most basic kind of query is a search for a single token on a single field. This query is implemented in Lucine's OAL.search.termQuery class. A term query is constructed from a term object, which is constructed from a field name and a text for the term, both specified as strings. This slide references query parser syntax examples. As previously mentioned, the query syntax includes basic field terms and modifiers for range matches, fuzzy matches, Boolean matches, and more. Lucine's default search scoring algorithm weighs results using term frequency inverse document frequency. As we know, term frequency means that high-frequency terms within a document have higher weight than do low-frequency terms. Inverse document frequency means that the terms that occur frequently across many documents in a collection of documents are less likely to be meaningful descriptors of any given document in a corpus and are therefore downweighted, thus filtering out common words. The API provides alternative scoring algorithms and a pluggable architecture that allows developers to build their own custom scoring models. Consequently, although the default is TF-IDF, the scoring method may be changed by overriding the scoring algorithm through modifying similarity factors, such as BM25, divergence from randomness, and information-based similarity.
Lucene lets you index any data available in textual format. It can be used with almost any data source as long as textual information can be extracted from it. You can use Lucene to index and search data stored in HTML documents, Microsoft Word documents, PDF files, and more. The first step in indexing data is to make it available in simple text format. You can do this using custom parsers and data converters. Indexing is a process of converting text data into formats that facilitate rapid searching. A simple analogy is an index that you will find at the end of a book. That index points you to the location of topics that appear in the book. Lucene manages an index over a dynamic collection of documents and provides very rapid updates to the index as documents are added and deleted from the collection. An index may store a heterogeneous set of documents with any number of different fields that may vary by document in arbitrary ways. Lucene indexes over terms, which means that Lucene searches search over terms. A term combines a field name with a token. The term created from the non-text fields in the document are consisting of field names and field values. The terms created from text fields are pairs of field names and tokens. The Lucene index provides a mapping from terms to documents. This is called inverted indexing because it reverses the usual mapping of documents to the terms it contains. The inverted index provides the mechanism for scoring search results. If a number of search terms all map to the same documents, then that document is likely to be relevant. Indexing can greatly improve the speed of information retrieval. The way it is used depends on the scale of information retrieval system. Large-scale information retrieval systems, such as Google, take advantage of the approach of inverted indexing. In Lucene, an index is composed of segments. A segment is made up of documents. A document is composed of fields, and many terms consist of a field. The index process of Lucene is started from the add document method of IndexWriter. As you can see, an example of the structure of Lucene index is shown on the bottom right. Here are 3 entries from an index of a collection of sample papers. Note that the document number here are Lucene's internal references to the documents. These IDs are not stable. Lucene manages the document IDs as it manages the index and internal numbering. which may change as documents are added to and deleted from the index. It let users perform fast keyword lookups and find the document that matches a given query. The analyzer's primary role is to segment the document and remove the stop words, which are no hope for retrieval, but occurrence frequency is very high, such as and ah, further separate semantic search words such as Chinese phrases, English words, and email addresses. Lucene can also provide us with two parsers such as Simple Analyzer and Standard Analyzer. Analysis is converting the text data into fundamental units of searching known as terms. During analysis, the text data goes through multiple operations: extracting the word, removing common words, ignoring punctuations, reducing words to root form, changing words to lowercase, etc. Analysis happens just before indexing and query parsing. Analysis converts text data into tokens, and these tokens are added as terms in the Lucene index. Lucene comes with various built-in analyzers such as Simple Analyzer, Standard Analyzer, Stop Analyzer, Snowball Analyzer, and more. These different ways they tokenize the text and apply filters. As analysis removes words before indexing, it decreases the index size, which it can have a negative effect on precision query processing. You can have more control over the analysis process by creating custom analyzer using basic building blocks provided by Lucene.
Hello class, my name is Mahendra Singh and I will present you the demo for the Lucene library. As Sherilyn and Jen mentioned that Lucene is an open source library maintained by Apache, is purely written in Java. It is extensively used in the Java based applications for text searching. Functionality of the search application can be explained in 4 steps. First, to acquire the data. Second, to build and analyze the document. Third, the indexing the document. And fourth, search query and result. Let's see all these steps in the demo. So for first step to Lucene to work is to set up the JDK. That's the Java JDK. You can download the JDK that's available on the Oracle site, and then you have to set the environment variables for the path and the Java home variables. As you can see here in the system properties and environment variables, you can set the path to the Java JDK, which is the installation path of the Java, and the Java home variable that is also set to the JDK, that is the location where the Java is installed. So after finishing the Java JDK setup, then next step is to download the Eclipse IDE and its setup. For downloading Lucene, we have to go to the Apache website, and here you can download the Lucene by clicking downloads and then choosing the server, and here it's for Windows it's the zip file contain the Lucene libraries. After downloading the Lucene, you can find the code libraries in the extracted folder, like it's under Lucene, and in that the code folder, and here it's the jar files. It's the latest version is the 7.1.0. I've downloaded the previous one also as 362, and I'm using this in this 362 as I'm having some problem rendering the functions for this latest library. So for this we'll be using this code library of 362. Now in Eclipse we need to make the new project, new Java project. So we click on new, in this new Java project we can give the project name like Lucene demo, and this is used default JRE. If you want to use any other version of JRE, because there is compatibility issues, so it's currently whatever installed in system, it will pick that, and then we don't need to anything else, and then next I think it's finish. So then here it's under this project has been created Lucene demo. I already created, so it will appear as twice. So under the source files we have to make over the new Java files, that's class files. So I already created the one, so here it's like our 5 files: indexer, Lucene constant, Lucene tester, searcher. That's the main file: searcher, indexer, and the Lucene tester. We have the Lucene constants file. This class is used to declare the various constants which we are going to use in our project. Then we have the text file filter file. This class is used to filter out the txt files from the directory. It will just accept all the text files only. If it contain any other files, it will just ignore it. Then it's the main indexer file. This is the main class used to index the documents, which will index our raw text data and use those indexes for the searching. The indexing is the core functionality of the Lucene. Here the analyzer will take the raw data as an input and will give tokens to index writer. An index writer then creates or updates the indexes for data and store the indexes at the directory location specified. In this file, it first creates the document. So this get document method is used to get the Lucene document from the txt file. It creates various key value pairs for indexing, like indexing the file content, indexing the file names, indexing the file path. But here we are interested in file content only, so we are adding it to the document and will use this file content for our indexing purpose. Then comes the index writer. Here it's the index writer. It creates the directory where indexes will be stored, and it creates the indexer object also, which will be used in indexing. Then this index file method is actually creating the indexes for the document, and these indexes will be used in the searching. Then this index writer method is there. It creates the directory where the indexes will be stored and create the indexer object also. Then comes the index file method, which is actually creating the indexes for the document that will be used for the indexing purpose and for the searching. Then comes the searcher file. The searcher file is the place where the searching will be done. So we need to make the query parser, which will parse the user entered query into a format which Lucene can understand. We need to initialize the query parser object with a standard analyzer, which will transform it into the word tokens. Then comes the index searcher. It searches the directory for the indexes, which our index writer has created the indexes and it's stored in the directory, so it searches the directory for that indexes. Till now we have created the query object, which is the result of the query parser. Then we will call the search method of index searcher. That's the core class for searching the indexes after indexing process. Now comes the top docs. It contains the result if the search matches. Like if query matches the content, then top docs will point towards the top end search results. So basically top docs act as a container which is containing the output of the search result. Now for testing our indexing and search process, we use the Lucene tester file. Here we are specifying the directory for storing index and the data. We give the search query, let's say example in like Kate. So Lucene will search the word Kate among the collection of the data set. For our demo, we use the 20 text files. Yes, 20 text files which contain the name, the email, the course numbers, GOB, etc. of the and other details for the students. So we use these data files, and as index process completes, the indexes will be created and stored in the index directory, and it will give the result with the documents which matches our search query. So let's run this Lucene tester. Right click on it and then run as Java application. So here we can see the output. It creates the indexes for all 20 files. It says the 20 files indexed, and with the query we have given the query Kate, so one document matches, and the document is the record number 20.txt. We can see the record number 20.txt. It has the word Kate. So this is how Lucene works. But if more than one document matches the search query, then Lucene will use the default scoring algorithm, which is based on the TF-IDF. As Sherilyn mentioned, we can customize this algorithm to change the scoring pattern as per our requirement. Let's change the query for, let's say, Paul, and let's see what it results. So run as Java application, and it says Paul is found on the record number 5. You can see like, yes, Paul is there. So let's see and change it to Patrick. This we have 2 times in our collection. So let's see how its results. Run as Java application. See, we give the results like 2 documents found, and that is the record number 14 and 21. So this ranking is based on this scoring pattern. That's the TF-IDF. So this way Lucene can search the given query word out of collection of documents using TF-IDF scoring, and results are very quick. So thank you guys.